here at the library, and we're so glad you're here today. It's my pleasure to introduce Diane Lincoln. Diane and I were just talking about books and reading, and one of my favorite quotes, and I'm going to not exactly quote it perfectly, but this is from a philosopher who said, "There are some great books that are written only for adults because of the content and the understanding required. But good children's books are written for everyone." So today, that's one of the things we're going to celebrate. Diane Lincoln is a former middle school science teacher who's also taught at the university level. She's currently a science writer and an active member of the Society of Children's Book Writers and Illustrators. And today she's going to be talking about her book, Science Discovery Files. Please join me in welcoming Diane Lincoln.
Thank you for that very nice introduction. This book started when I was a teacher and my students, being middle schoolers, would be unwilling to accept just facts you would give them. And they'd say, "Mrs. Lincoln, how do we know that?" So this book answers some of those questions. The book is it has 10 chapters that are standalone stories. So you could read one out of order, whatever, but they all answer a question. About the book, Sean Carroll, who's a famous writer of science books, he said that my book is an interesting and important and mapped out from PBS space-time. He said that, he said nice things about me. He said that I'm a brilliant teacher and masterful storyteller. I'm not sure I would go that far, but I do hope that you enjoy the stories. Like I said, there are 10 stories in the book, but I don't think I'll be able to cover all 10 today, but I'll give you a nice taste of what's in the book. Okay. We'll start with Mapping the Cosmos by Henrietta Swan Leavitt. Anybody know of her? Oh, good. Okay. All right. She's the one who taught us how big the Milky Way is and beyond. Okay, I saw this picture. This is not Henrietta's actual house. All right, her house is long gone. But this one was built circa 1870, so it's sort of when she would have lived in a house like this when it was new. And the reason I thought this was an appropriate picture is because there's many stories of her growing up in a white clapboard house, and she and her mother would sneak out the window onto the roof to look at the stars. So that's why I like this old house. She lived in a home similar. She grew up in Lancaster, Massachusetts in 1870. She was of Puritan descent, and she dreamed and marveled about the stars. Now, in those days, nothing was known about the stars. We thought the universe was the Milky Way. That was it. And places that we've since learned are entire galaxies. They thought was just dust in the Milky Way. So Henrietta always dreamed of being able to look in the sky and know whether a star was far away and really bright, or if it was closer and dimmer. Back in the day, in the 1800s, very few women went to college. There were very few colleges that allowed women to attend. But she did. She went to Oberlin College, and then she went to Harvard University School for Women, which is now called Radcliffe in Massachusetts. Because she was really skilled at mathematics, she was hired by the astronomy department at Harvard as a computer. Okay, you've heard that story before. Before electronic computers were invented, they often hired women to do mathematical calculations, and that was her job. When she was working, she took a trip up to Wisconsin to visit her father. And while she was there, she got very sick. And she started to lose her hearing. And she would fight that battle for the rest of her life, becoming more and more deaf as the years went on. She loved her job so much that she wrote a letter to her boss, Edward Pickering, and asked him to send work to her that she could look at while she was recuperating. Okay, so she was really interested, like I said, in determining how far away stars are. She took only one astronomy class in college, and she learned that the question about whether a star is huge and far away or whether it's closer and smaller was partially answered by parallax. Okay, so what is parallax? All right, we can try it. All right, so hold your finger out in front of your face. All right, very far. Okay, and then close one eye and close the other. And you see how the background jumps back and forth? See that? Okay, now move your finger closer to your face and do the same thing. And you see how the background jumps even more. Okay, so looking through one eye and then the other can be used on Earth too, as Earth is in one position, and then look at a star from another position is like looking at something nearby with one eye in one position and the other eye from the other position. So here's how it works. So in the first picture, you see Earth going around the sun, and in the summer and in the winter, you look at a star that's close, and the background behind that star is very different in the summer than it is in the winter. But if you look at that star in a faraway star, you see that the background stars don't change so much. Now, unfortunately, that only works to about 200 light years, maybe 300 light years, okay? Because most of the stars that are out there are much, much farther, and parallax won't work. You can tell exactly how far a star is by using parallax combined with some simple geometry of angles, and they can tell just how far away it is. Okay, next thing. It's limited to 300 light years. Okay, so in addition to working as a computer, one of Miss Levitt's jobs in the astronomy department was to record the brightness of stars. So she did this. It's a drawn picture of Miss Levitt. She did this using a light box. This was before electric lights. So that bottom plate is a mirror that would collect the light from the room and shine it up into the plate she's looking at. The plate she's looking at is one of these glass plates with a blizzard of dots on it, and those are all the stars that she looked at. This is one of her actual plates, and you can see her notes on it about how bright and how big the stars are. Some of the other tools that she used included, of course, a handheld magnifying glass for looking at those little dots of stars. And then the second picture, those are things that the women who were doing the job actually invented, and they called them fly spankers because they look like little tiny fly swatters. But what they are is pieces of glass with dots on them, and they would use those pieces of glass, put it on top of what they were looking at in order to determine how big the dots on their plate were, how big the stars are. So that way it would stay a standard size. Okay, and then also she would use a little magnifying glass that she wore often around her neck. So here's Mr. Pickering and the women who worked as computers and who looked at the stars to measure their brightness and so on. Henrietta Leavitt was so proud of her job. She made 30 cents an hour. Now that doesn't seem like a lot. She made less than the men who were scientists doing similar jobs, but she made as much as a factory worker. So 30 cents an hour was not too bad, less than the men, but still. And you can see her in the back with the broad chin, that's Henrietta. And in front of her at a table is another woman named Annie Jump Cannon, who was also a famous astronomer in her own right, but that's for a different day. And Mr. Pickering, of course, is in the back. She was so happy about her job. She was so proud because she was one of very few people in all of New England who knew anything about the stars in the southern hemisphere. This is a picture of the Small Magellanic Cloud. There's a small and a large Magellanic Cloud that Magellan used to circumnavigate the globe because, of course, when you get into the southern hemisphere, you can no longer see the North Star, but you see the Southern Cross and all that, the Magellanic Clouds. So she was very proud that she knew about that. And the pictures were taken mostly in Lima, Peru. Okay, so here she is doing her job. And another task that she had to do, oh my gosh, talk about tedious. She had to look at the same slides over, not the same slides, but the same stars, pictures taken over and over on different days. Because what she was looking for is stars that change their brightness, that are called Cepheid variable stars. So they go from bright to dim and bright back again. And she would observe that. It's different, I have to say, it's different from the twinkling of stars. Twinkling stars are caused by our atmosphere, but those stars that get bright and dim is what she was looking for. By 1908, Leavitt had recorded the brightness of, believe it or not, tens of thousands of stars. And she identified 1,777 Cepheid variables in the southern hemisphere. In her notes, when she was recording her catalog, in her catalog, she noted that there might be a relationship between the brightness of a star and its cycle time, the time it took to go from dim to bright. So with permission from her boss, Mr. Pickering, and I keep saying his name because I think he's also one of the heroes of this story. With permission from her boss, she looked into the relationship that she thought might be there between the brightness and how long it takes to go through the cycle, because this could be the key to determining whether stars were large and far away or smaller and close. And Mr. Pickering said, yes, go for it. Just, study them. And she chose 25 variable stars in the Small Magellanic Cloud for her study. Now, the reason she chose these 25 stars is because they were all taken on the same astrograph. So it wouldn't be like comparing one photographer's picture to another. They were all taken in the same place. And they were too far away for parallax to measure. And thirdly, because they were all in the same Small Magellanic Cloud, they're probably all the same distance from Earth, or relatively the same distance. So as she did her study, and she looked at each star and each star's brightness, and she started looking at it, it's like, wow, what she suspected was true. There seems to be a relationship between brightness and how long it takes her to go through. Now, this is the paper that details what she did. And I know it's hard to see from out there, but there's no author written on this paper, because at one time, only men could file papers. So Mr. Pickering filed the paper, and notice what he wrote in the first line. He said, and he didn't put his own name on it, which is why I think he's a hero. He could have easily taken credit for what she did, but he did not. In the first line, he wrote the following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt. Okay, this is her actual, what she saw. She saw that, and she knew this was the answer to how to determine whether a star was far away and bright or close. She knew it was the answer, and everybody there in the astronomy department, including Mr. Pickering, knew when he saw her results, and yet he gave her credit for it. Henrietta Swan Leavitt, a deaf woman, she was deaf by that time, had provided astronomers with what they called a standard candle to measure the distance of faraway stars. Astronomers knew to do the following. If you use parallax to measure the distance of nearby variable stars that have the same cycle, takes the same amount of time to go from bright to dim, and you know how big they are, that will give you the actual brightness of the faraway stars that you can't measure with parallax. And once the actual brightness was known of the faraway star's distance, you could calculate it mathematically. Okay, I'll give you a minute to think about that. You use the variable stars that you know their distance, and then that'll tell you the real brightness of the faraway stars. Okay, this is how it works. It's using the inverse square law. Okay, so imagine that that first box represents how bright a star is as we see it from Earth. If the star is 1/4 that brightness, it's 2 times the distance. If it's 1/9 the brightness, it's 3 times the distance. 4 times would be 1/16 the brightness, and so on and so on. And that's how the inverse square law works. As dimness squares, the distance multiplies. So with mathematics, they could calculate how far away the stars were. Oh, and just as a footnote, Newton's law of gravity and Coulomb's law of electric current, they also use the inverse square law. When 2 heavenly bodies are a certain distance from each other, gravity affects them the same way as the inverse square, as the light appears. Okay, so here's a picture of the small and large Magellanic Cloud. Miss Leavitt did live long enough to learn that her small Magellanic Cloud was about 200,000 light years away. So we could now measure 100,000 times farther than we could before. And then we learned that the large Magellanic Cloud is a little bit closer. And that bright spot right there, that's actually a star. That's significantly closer. It is 13,000 light years away. So, using Leavitt's technique, it just opened up an entirely new understanding of the universe. Okay, we learned that the Milky Way is not the entire universe, and things that we thought were dust clouds in the Milky Way turned out to be faraway galaxies that are as big as the Milky Way. We also were able to calculate the size of the Milky Way, and a man named Shapley, he calculated it using Leavitt's law to tell where the sun is located within the millions of stars in the Milky Way. We also learned using the Leavitt's technique that the universe is expanding. And we can now measure up to 200 million light years away. So far that it takes light 200 million years to get here. We're looking at stars that might not even be there anymore. It's kind of cool. And we're still learning. Each chapter in my book has a further reading and some additional information that was not exactly relevant for the story. But anyway, Miss Leavitt's Stars is a good book to read, and there's an additional information. That picture there is her with Annie Jump Cannon. Okay, and then also each chapter in my book, for those of you who are teachers or no teachers, please tell them. Part of the reason that I wrote this book was so that friends could use it even as a sub-plan, give students, have them read about Henrietta or someone else, and then there's a discussion question. So the discussion question is, few people hired women as scientists, but Pickering did, and he paid them less than the males. And then the discussion question was, did he take advantage of the women, or was he helping them? So I'd say a little bit of both, but all right. So that's my book, and that's the story, one story, the one about Henrietta Swan Leavitt. Before I move on to another story, does anybody have a question? Yes?
I've seen that Leavitt's Law mentioned when they talk about the age of the universe, and I know that there's a discrepancy. Is that simple to explain? The difference between using cosmic background radiation versus the parallax.
Okay. The question was, they use Leavitt's Law, and there's some discrepancy that they see between what we know from Leavitt's Law and cosmic microwave background. And she asked me if that's easy to explain. The answer is easy. No. No, it's not easy to explain. And there has been another way to measure stars even farther than Leavitt's Law, and it's based on the time it takes for supernovae to go through their cycle. So there is another step in the cosmic ladder beyond Leavitt. Okay. Question? Yes.
Okay, I always had thought of the universe and everything being traced first in Oriental or other culture. Is this just really emphasizing the America, United States, European, that grade, or is it also including some of that background that they had?
Okay, the question was, is it just an American view? And the answer is no. In the scientific community, scientists around the world share what they learn. So,
I didn't know at that era.
okay, all right, no, even back then, scientists shared what they knew. Sometimes the transfer of information took a little bit longer because without modern communication, but yeah, scientists are good that way. Okay, want to go to another story?
Yes.
Cool, all right. This one, completely different, okay? This is the story of Alexis St. Martin and Dr. William Beaumont. This story takes place relatively close to home, on Mackinac Island. Takes place about exactly 200 years ago, in 1822. And it's easy to imagine what the place was like in 1822, because if you've ever been to Mackinac Island, you know that there are no cars, there's just horses and bicycles. There's also a lot of untouched natural places where you can look out and just imagine a canoe going by. 1822 is right there. Fort Mackinac is on a high hill, and it's a museum today. But at one time, it was a very strategic location between the two countries, between Canada and the United States. And the cannons are still pointed out toward the water. Fort Mackinac was the first encounter of the War of 1812. And in that bloody battle, we actually lost Mackinac Island, and we lost the fort to the British. So between the War of 1812 and the Civil War, there was a time of peace. which is when our story takes place. And yes, we did get the fort back before the Civil War, and troops from Fort Mackinac actually were sent to battle in the Civil War. But between those times was a time of peace. It was before the California Gold Rush and when the United States had only 24 states. Okay, so now you can picture the time, hopefully. Trappers and fur traders came from the woodlands of America to the south and from the forest of Canada above to the north to trade on the island. And you can see the island is right in the middle, right there, Lake Huron. This is a place where Native Americans, Frenchmen, and U.S. soldiers lived and worked together on the island. And I drew that picture. But I couldn't find any pictures that would show that the fur trading company, it's a trading post, and to the right of it you see that was a farm. Almost all the land on the island was used to farm for the soldiers, to provide food for the soldiers that lived up in the fort that you can see up in the upper right corner. Okay, Alexis St. Martin. He was a young trapper from Canada who traded pelts and wares at the American Fur Company trading post on Mackinac Island. His job was to set traps out in the woods and then come back sometime later and take the animals, skin them. He would eat the meat from the animals. He didn't have to pack any food, no canned goods, He'd eat the meat and leave some of it for the forest animals. And then he would take the pelts and put them in his canoe and go across the icy cold waters. If you've ever been up there in Lake Huron, it is cold. And he would make his way back and make his way to the trading post. So on the day that he arrived, a spring day, he arrived at the trading post and it looked like this. The little building on the left is still there. So if you go up there, you can go in and look around. You see the little building has two fireplaces, absolutely necessary. It gets so cold. And then on the right side of the building was all retail space where the people would come and bring their pelts and they would trade them for pots and pans or dishes or blankets, whatever they might need. So no one could predict what would happen next when Alexis St. Martin went into this quiet trading post on the island. But another person, a patron who was also trading pelts, set his shotgun on that counter and kablam! Alexis St. Martin was shot right in the belly at close range. The townspeople ran up that steep hill to the fort to get the army doctor, who grabbed his bag and ran back very cautiously because it was so steep. He didn't want to fall. When Dr. Bowman arrived, he found Alexis lying on the floor bleeding, of course. And he had a wound in the side of his torso that was 4 inches in diameter. Think about that, 4 inches. Yeah, 4 inches in diameter. He had a hole in his gut. Inside the hole, the doctor could see a broken rib and a damaged lung. So the skillful doctor amputated the rib and tucked the lung back into place. Then he removed the shotgun pellets and stopped the bleeding and dressed the wound. Now you might be thinking, okay, that probably happened a lot between 1812 and the Civil War. An army doctor would have to patch up a wound, right? Oh, this was different. It was too dangerous to move Alexis up to the fort, so a cot was set up for him at the trading post, and the doctor came down to visit him every day. The trouble was that every time Alexis ate, the food would pour out of his belly onto the onto the wrap. And when he got a fever, and of course, that would follow after such an injury, the medicines would also leak out. The doctor didn't say so to anyone at the time, but later he reported that he didn't expect the young man to live. So while he just made the man comfortable, he kept redressing the wound, and he came down to visit him every day. A year later, the wound was smaller. It was 2.5 inches, and the edges all around had healed, leaving an opening to his stomach. St. Martin's stomach could still be, it could be seen. And some months after that, something truly incredible happened. Nature just decided to fix the wound itself by a fold in the stomach lining fell down and covered the wound. So now the food could stay inside, and Beaumont no longer had to apply the bandages. But by pushing on that little flap that was made by Alexis St. Martin's stomach lining, you could push on the flap and you could still see inside of his stomach. Pretty bizarre, yeah, I know. And this picture was how Dr. Beaumont represented the hole in Alexis' stomach. So Alexis was in good physical condition, but it was not advisable for him to work alone in the woods anymore. So this is where they struck a deal. Comes into play. They struck a deal that Alexis agreed to work as a handyman for the doctor, and in return, the doctor would give him a steady paycheck and take care of him, provide medical help if he needed it. And in exchange, the doctor could do experiments with Alexis's stomach. Yeah, Alexis agreed to let him do it. And in 1823, there was very little known about digestion. It's just that food goes in, it comes out. They didn't know anything else. So Beaumont performed many experiments and kept meticulous notes. He placed food on a string and put it into Alexis's stomach, and then at a given time, and you can watch the watch, meticulous notes, then he would pull the string out and observe what happened by weighing the food and measuring it. He learned that digestion was caused by acids. He learned that the acid was secreted by the stomach lining. He could actually see it. And science. He touched the inside of the stomach with his tongue and learned that he could only taste acid when there was food in the stomach. So it was the arrival of food into the stomach that triggered the production of acid. He also took some acid out of St. Martin's stomach and did experiments on it. In jars, he would put food and what have you into the acid and see what happened. And he also learned that the temperature inside your stomach is 1 degree higher than the rest of your body temperature. For almost 10 years, Alexis worked as the doctor's handyman before he decided it was time to go back to Canada. What happened was Dr. Beaumont got transferred to St. Louis, and Alexis said, no, I need to go back home. So he went back home to Canada. And during the 10 years that they worked together, Beaumont took his patient around and showed him to other doctors so that other people could learn about digestion. Beaumont wrote a book with this intimidating title. It's called Experiments and Observations on the Gastric Juice and the Physiology of Digestion. And the book earned him the nickname the Father of Digestion. So what happened to Alexis? Well, when he returned home, he married and had a family, and he lived to be an old man. He didn't die until 58 years, after his near-fatal accident. And we don't know exactly how old he was when he had the accident, but he was a young man, possibly late 20s, early 30s. His contribution to medical science was great. They call Beaumont the father of digestion, but if you ask me, the real hero of this story is Alexis, because he could have just gone back home and didn't have to allow a doctor to do all these experiments, but I think he contributed much to our knowledge. Okay, and as I said before, there's further reading suggestions and additional information that doesn't have anything to do with the story. For this story, I would tell people to read Dr. Beaumont's book. It's written in pretty straightforward English, and you can get it on the web. And he tells the whole story about how he amputated the rib, and how he tells every single step of what was happening as he went through this. And a little bit of information about the island is that if you want to see what the island looks like, there's a movie called Somewhere in Time, starring Christopher Reeves and Jane Seymour, and it was filmed on the island. And I don't know if any of you remember Paul Cook. He was a Geneva resident, and he had a small part in that movie. He played the doctor. So I see a hand up. Paul Cook, yeah, he was a card. Great guy. Okay. So, and this is the discussion question. The question is about ethics. Was what Dr. Beaumont did ethical? You know, do you think experiments on humans should be allowed? And to what extent and with what restrictions? These are things that students could talk about. Questions? This is only one of the chapters of 10 in Science Discovery Files. Okay, yeah.
Did Beaumont also study the juices, the acids in the mouth?
Okay, she asked if Beaumont studied the juices in the mouth, and I believe he did. I believe he did, yeah. Because that's part of digestion too. Okay. The book is written, like Stacy said in my introduction, the book is written at 7th grade level, but I think anyone can read it. A precocious 4th grader through high school students could read it. Parents could read it too, pre-readers. Maybe skip the story about the kablam in the belly. But parents could read it to pre-readers, or grandparents could read it themselves and not let their grandchildren know where they got that wonderful information. Just be the wise sage that knows all these stories. Okay, so, all right, we'll move on to something different. Third story out of 10. This is about a father and son who solved a mystery. Walter Alvarez, pictured on the right, and his father Luis Alvarez. Anybody know of them? Okay.
I read the book.
Oh, okay. Walter, who the story is about, the younger. He was born in Berkeley, California in 1940. He was actually born on my birthday, so that's kind of cool. And as a child, he learned about rocks. He loved to learn about rocks. His mother would take him and his sister out to look at the rocks. And he learned about igneous, sedimentary, and metamorphic rocks. Igneous, of course, is from fire, like ignite, you know, the lava rocks. And then sedimentary is from sediments that get pounded together. And metamorphic, of course, are changed rocks. His interest in rocks came natural to him. He understood that older rocks would be found at the bottom layer of rock layers, and then they would get progressively younger and younger. And he also learned about mountains, that there are places in the mountains where earthquakes lifted up really old rocks, so he could see some of the really old rocks. After high school, he got a BA in geology from Carleton. Then he went to Princeton, where he earned his PhD. He did his PhD thesis in South America, and then he worked as he worked in the Netherlands and in Libya for an oil company. A geologist is important to an oil company, you know, being able to find all that oil. And then he spent time in Italy. That's a picture of Vesuvius in the background there. He spent time in Italy. So he was not a young man. Okay, he was 30 maybe, you know, not a recent college graduate, I should say. And he loved to read the story in the rocks. In 1978, he was hired by Columbia University in New York to study paleomagnetism in Italy. Now, paleomagnetism is one of those words that would intimidate my students, but all it means is magnetic changes in the rock that happened a long time ago. And to do this, he went to Gubbio, Italy. Now, I'm telling you, if I sell enough books, I'm going here. I'm going to Gubbio. The city was there before the Romans. Okay, and it's got this canal that runs through it with all these gorgeous bridges, and there are streets that were made for, they're like steps for horses to climb up. But the reason that Walter Alvarez went there was to study the pink limestone in the mountains back there outside of Gubbio. So he took his backpack and he hiked into the canyons, and he had, you know, the usual things that you bring with. He had his knapsack with a compass and paper and pens and his little rock hammer. And he made a drawing of the wall that he approached. And on the drawing, he included the well-known KPG boundary, which is the boundary between the Cretaceous and Paleogene era. But while he was there, he kept getting distracted. I mean, he was looking for magnetic changes, all right? But he kept getting distracted by foraminifera that we call forams in the rock. Forams are tiny, they're in sand. If you look at sand under a microscope, you'll see little, what do you call it, like seashells and stuff. Now, most people might be surprised to find seashells up in the mountains, but that's not what surprised him. That's not what surprised him at all, because he knew that that mountain range at one time was the bottom of an ocean, and it had been lifted up. In our Rocky Mountains, you can also find seashells and fish fossils up at the top. It's kind of cool. But that's not what distracted him. What distracted him is that below the KPG boundary, the forams were bigger and more varied. And then on the top of the KPG boundary, they were smaller and there was less variety. So he thought it would be cool to determine how long it took the line to, if he could determine how long it took the line to form, he could determine how long it took for the forams to change. So he decided to measure iridium in the line. Iridium falls to Earth at a constant rate. So he thought that if he could measure the rate of accumulation, he would know how long it took it to change. So he took a sample of the KPG boundary to his father. And his father found, you know, he could measure the iridium in the rock because he was a physicist. And by the way, he's a Nobel Prize winning physicist, but this is Walter's story. Anyway, they found that there was 30 times more iridium in the layer between the Cretaceous and Paleogene boundary than there was in the rocks above it or below it. So they thought, well, maybe this change was unique to Gubbio. Maybe the KPG boundary, which, by the way, is all across the Earth. Anywhere on Earth, you go to Texas, you go to China, and there's that line. It looks like a chalk line between the two boundaries. And it was a well-known boundary because paleontologists had known for 100 years that you should never look for dinosaur bones above that line. It was like a sign that said, dig here, not here. Okay, that line. So we thought that, well, maybe it's just in Gubbio that there's so much iridium in the line. So they wrote to scientists around the globe and asked them to take samples of the line, of the clay-like material in that line, and see what it's made of. So this is a picture of a famous place to see the line. That dark line, it's like totally obvious right there. Wait, more like right there. You see? All across, you can see the KPG boundary. It's in Copenhagen in Denmark. Anyway, what was reported was that what they found was that the iridium was in every single place all around the world. There was this huge amount of iridium in the line, in that clay line that separated the two periods. And the two men, here's Walter and his dad, Luis, they wondered, could this be a global disaster? But that was the hardest question to answer because until then, no one had ever even heard of global disasters. It just wasn't scientific to think that way, you know? Could this be? And if it were a global disaster, could it be the same thing that caused the forams to change, that created the mass extinction of the land animals? And what type of disaster could have caused this? Well, Luis, being a physicist, was very aware of what a nuclear bomb would do. And he said, well, it looks like it could be nuclear, you know, but that couldn't happen all around the globe. They couldn't, but then they had to face the fact that the iridium comes from outer space and is mostly in asteroids. And the reason it filters down to Earth the reason it filters to Earth at an expected rate is because it does come from outer space. So they put their theory was published in the 1980 Science magazine. They said that they believed it was an asteroid that killed the dinosaurs. But even then, even though they had all this proof, nobody believed them. Because the problem was, where is a crater that's big enough to have been hit? You know, Earth was never hit by an asteroid that big. But finally, in 1991, they discovered the crater. The crater is right off the coast of the Yucatan Peninsula, near a town named Chicxulub. Now, of course, it's been covered up by many layers of soil, and much of it is under the water. But now, with our technology that we have, that we can see underneath the water and under the layers of land, now we know there's a huge, huge crater down there. So now, today, now that we found the crater, most scientists accept that it was an asteroid that killed the dinosaurs. But my students, they would always ask me, how do we know that, Mrs. Lincoln? How do we know that? You just tell them that an asteroid killed the dinosaurs and they wouldn't accept that. So anyway, a good book to read along with this chapter is T-Rex and the Crater of Doom, written by Walter Alvarez himself, who is a current professor at UC Berkeley. And he tells all about, most of the book is about hunting for that crater. Okay, also the additional information included in the book is a description of the pink limestone and a comparison between Meteor Crater in Arizona and the Chicxulub crater. The Chicxulub crater is like 100 times bigger. And yeah, right? And you all know how big that is. And the pink limestone's a sedimentary rock. So you wouldn't normally find any changes that are magnetic in that rock, except that the pinkness is caused by iron. So that's what Walter was initially sent to Gubbio to look for, that pink limestone. And then there's a discussion question that I rather like because it tells the students all the different careers that are out there for them. There's a lot of people who look for secrets hidden under Earth's surface. Paleontologists look at animals from the past and what they were like. Archaeologists study early humans, their architecture, and how we settled around the globe. And geologists like Walter learn about Earth's past by uncovering evidence of earthquakes, volcanoes, glaciers, and like that. And then, of course, I'd ask my students, which of those jobs would you like to have? Because I'm hoping that they would all grow up to be scientists. Because believe it or not, there's still a lot out there that we just don't know. And that's Science Discovery Files. We have only about 6 minutes. So, yes?
You said iridium falls to the earth at a constant rate. Where does that come from? Is it only asteroids or other sources in the universe?
Okay, asteroids, mostly, just dust from things that bang into each other. And most asteroids or most meteors that hit the ozone, that hit the atmosphere, will burn up and they'll come down as dust. And so that's the dust that gets collected at a known rate. Did I answer your question?
Yeah, but it doesn't seem, to me, it doesn't seem logical that it would be a constant rate because the number of asteroids hitting the atmosphere varies.
Not by a significant amount, really. Well, asteroids though are pretty, asteroid chunk is pretty big, but meteors fall all the time. Maybe you know about that one in Tunguska in Russia that destroyed a forest, or just recently, when was it? 2009, maybe? When that other one hit Russia and there's videos of it going across the sky. Yeah, they fall at a pretty constant rate. When you're dusting in your house, yeah, it comes from outer space. A lot of it. Well, a lot of it is from traffic, but a lot of it is from outer space too. Okay, questions? Yes.
So if this asteroid killed all the dinosaurs, did it also kill all other living life?
It killed about 90% of the living things on the planet. The forams, those little tiny things that Walter saw, they changed. A lot of them went extinct, and only the smaller ones survived. And if it weren't for that asteroid, by the way, killing the dinosaurs, humans never would have evolved, because we couldn't have evolved with dinosaurs competing for resources. So yeah, it killed a lot. And there have been other extinctions too, but that was one of the big ones, and that's the one the students like to hear about.
Yeah.
Okay, do we want to run through another one real quick, or are we?
Do you have time?
Sure, let's just do it real quick. I can't do my usual hemming and hawing. Okay, this next one is called It Didn't Seem Possible, and it's a geology one too. There was a drill ship called the Glomar Challenger that set out to sea in March of 1968, and it could reach through 5 miles of salt water and take samples from the bottom of the Atlantic Ocean. When the ship set sail, most of the crew never heard of this guy named Alfred Wegener, a German scientist who had died 30 years later. But geologists who knew of him celebrated when the ship made its findings. In 1912, That's a picture of Wegener there. He was studying the atmosphere in Greenland, and he read a paper that said that fossils of, I can't think of the word, fossils of plants like ferns, tropical plants had been found there, and he thought, no. He knew that when he goes outside, you could see his breath. There's no way tropical plants could form there unless there was some kind of prehistoric climate change. So he decided to look and see if he could find evidence of climate change, prehistoric climate change. And what he learned is that there are scratches left by glaciers in tropical Africa. That's just as weird as ferns in Greenland. So he took a look at the map and, trying to figure out how these areas could have undergone such a change. And he noticed what school children often see when they look at the globe, and that is that if South America could scoot across the ocean, it would fit like a puzzle piece right in with Africa. So he thought, wow. So he started to learn as much as he could about those two areas that seemed to fit together. And he read an article about this little alligator-type creature that was found on both shores where they seemed to fit. And he thought to himself, sitting there puffing on his pipe, if this little guy could swim all the way across the ocean, there would be fossils of him all over the place, up and down the coastlines. But there weren't. So he read more about that area and learned that the rock layers on those continents so far away from each other matched up layer for layer on two sides of the Atlantic. So he said, wow, that's some pretty good evidence that those two places were once connected. But nobody would believe him. They thought that the evidence was intriguing and interesting, but they couldn't imagine a continent plowing across the ocean. And then the Glomar Challenger revealed the age of the ocean. And what they found is that in the center of the ocean was some of the newest rock they ever saw. And now that was the missing piece that was needed when applied to Wegener's evidence. They realized that what happened was that earthquakes created a rift in the landmass. And the Mesosaurus fossils were left on the African side, and some were left in what would come to be known as South America. Lava bubbled up through the cracks, and it hardens and it pushes the two land masses away. And that continued for millions of years. And as it got deeper and wider, the crack filled up with water and became the Atlantic Ocean. And to this day, the Atlantic Ocean gets wider by 2 inches every year. 2 inches? No, 1 inch, 2 centimeters every year. And it's also happening at the Red Sea, where it's pulling apart because lava is bubbling up underneath. Turns out that it's happening all over the globe. The plates are moving. Some are moving away from each other, some are bumping into each other, like in the Himalayas. The Indian plate is banging into the Asian plate, and the Himalayas are getting taller and taller every year. And it's an entire science that today we know as plate tectonics. So Alfred Wegener's idea wasn't so weird after all. And there's some suggested reading. And also what the Glomar Challenger discovered was that Earth's poles, the magnetic poles, south and north, flip probably about every 10,000 years. I know. And those were the changes actually that Walter Alvarez was looking for in the mountains in Gubbio. He was looking for those magnetic reversals when he discovered the forams in the other story. Okay, but the poles flip, and maybe it'll happen in our lifetime. It would be pretty cool. All of a sudden your compass would point the wrong way. it would take us a little while to get used to the change, but I don't think anything terrible would happen, like some science fiction stories say. And then the discussion question for that one is: if you were around during Wagner's time, would you believe him? Would you search for more evidence? You know, how would you behave? Would you be like the other scientists and say, well, I'm willing to listen if you can tell me how those continents moved, then we'll talk. And that's Science Discovery Files. And I went a few minutes over, Stacy, sorry. I thought I could do it in 5. Oh well. Any questions about plate tectonics, moving continents, Wagner's strange but true idea?
Well, yeah, is this connected to climate change? Or
Oh no, because
No.
he decided that it wasn't a prehistoric climate change that occurred.
okay.
It was continents moving from one climate to another that caused the change. Okay, so Greenland, or where they discovered the fossils, was probably in a warmer climate at one time.
Amazing.
Yes. Okay, maybe I went through that one a little bit too fast, but
No, maybe it just takes me longer to get that.
okay. Any other questions? Okay. Well, yes.
I just have one, going back to the asteroid, hitting the Earth, and the location, the crater in the Yucatan, would they ever go down looking for the actual chunk of metal or whatever it was?
I think it was, now I'm not sure, but I think it was the chunk of metal that remains that they detected at first with the ultrasound and looking for magnetic changes and stuff. So yeah, there's a bit of it still left down there, but mostly it was the crater. The crater's huge, absolutely huge. Other questions?
I
No?
do.
Yes.
With current climate change, does that affect the plates moving?
No. The question is, does current climate change affect the plates? No. There is such a thing as current climate change. But it's not affecting the plates. The plates are big hunks of rock that float on the mantle of the Earth, which is liquid. So they're just floating around and bumping into each other. And if you watch a video of lava cooling, it looks kind of like that. The top crust, it gets a crust, and then the crusts bump into each other, and that's very similar to what's happening on Earth. And Earth is not getting bigger either, because the Atlantic Ocean is getting bigger. The Earth stays the same size, it just puts pressure somewhere else where a plate will run in and make a mountain range. So no, it has nothing to do with today's climate change, which is absolutely 100% real. Other questions? Yeah.
This is just a comment. You make science so much more interesting than when I went to high school and grade school.
Well, thank you. I'm glad to hear that. I tried to make it interesting for my students because I don't want them to be intimidated by the big words, or that it's just stories about human beings that are curious and follow a notion to learn something. And science is just a collection of everything that we know. Yes?
Where did you teach?
I taught in Naperville for a very short time, but then at the high school, and when I had my son, I quit teaching for a while, and most of my career I spent in West Chicago at the middle school. And now I wrote a book, because even though I'm not in the classroom anymore, I want to continue teaching because I think science is really, really important.
And interesting.
And interesting, thank you, yes. Yes, it is, it really is. Okay, and there's, so I went through 4 stories, there's 6 more in the book. There's a story about how we knew that CFCs were destroying the ozone. There's a story about how we know about radiation, what it is, how we discovered it. I can't think what else. Oh, how a woman in Asia discovered a brand new treatment for malaria when malaria was becoming immune to quinine. And I don't know, I'm missing some, but anyway, there's a whole bunch of stories in there. Okay, anything else?
Thank you very much.
Thank you. Thank you.